Okay, hello everyone. Welcome back to the Intercontinental Seminar Series on Gravity and Cosmology. So today we are very happy to have our speaker, Diego Rubiera-Garcia from Complutense University of Madrid in Spain. And he is going to talk about theoretical properties and observational discriminators of black holes in Palatini theories of gravity. So during the talk, you are welcome to ask questions if you have some, and also you also feel free to ask questions after the talk. So please, the stage is yours, Diego.
Thank you to you for the kind invitation to talk today. Can you hear me? Yes?
Yes.
Okay. So thanks for the kind invitation to talk today. So I'm very happy to join you in these discussions of physics. So today, because I offered to you two options or things to talk, so I'm going to talk about one of them, which is to try to combine, because I work in theoretical gravitational physics, but because our field has, in the last few years, because we have data about new phenomena in the universe, so the field is evolving very quickly to make contact between theory and observations. So that's my main aim of research in the last few years. So in this talk, I'm going to tell you about how to, our attempts on how to connect theoretical properties of a specific modification of gravity, which are called Palatini theories of gravity, with some observational discriminators, in this case regarding black holes. So I'm going to talk a little bit about this, about the motivations and how to bring closer theory and phenomenology in different scenarios. Okay, so let me pass the slide. Okay. So the context in which we are moving is general relativity, black holes, the gravitational interaction as we know it nowadays, described by general relativity. So you know, a metric, a connection that define the space-time, which events happens, and gravity and matter and wave together in order to describe the gravitational interaction. And this description has been extremely successful because many different experiments, every experiment according to today has not been able to disprove the theory, so has been very successful at different levels. And one of its core predictions of interest to this talk is the prediction of black holes that emerge out of gravitational collapse of full exhausted stars, and current data favor strongly the interpretation that black holes are real objects in the universe, are not simply solutions of the field equations, because you know, general relativity, its field equations will have extremely large number of mathematical solutions, but most of them does not have any meaning in the real universe, but black holes do. We have three different ways of supporting this sentence. First, the ancient one, which is kind of indirect evidence, is regarding the X-ray spectroscopy that we do around about the accretion disks that surround black holes. And so these are tests based on purely astrophysical reasons, assume that there is a black hole in the core producing different effects of astrophysical origin, and studying the properties of the disk, we can get indirect proof of the existence. But in much more modern times, we have had two independent sets of observations. The first one based on gravitational waves that are supposedly originated from the merger or the collision or the coalescence of two black holes or a black hole and a neutron star, and produce a trail of gravitational waves that we have been able to detect. And on the other hand, we have the imaging, or what is called the shadow, which is nothing but the accretion flow that surrounds the black hole, that illuminates the object. The gravitational field of the black hole bends these light rays and produces a characteristic image in our devices that we call the shadow, because there is an internal central dark area surrounded by some luminous matter. These two means are compatible with both astrophysical and black holes, and with supermassive black holes at the heart of two galaxies. Okay, so these are two independent means by two independent messengers that tests black holes in two different regimes: astrophysical black holes on one side, supermassive black holes on the other. Okay, so this is taking part of the four that is called multi-messenger era, which is doing astronomy of black holes with neutrinos, light rays of different source and gravitational waves. So we can test nature of, in this case, black holes according to different means. In order to test the nature of these objects, we need to first have clear in mind what general relativity predicts about these objects. And from a purely mathematical perspective, general relativity tells us that there is a single type of black hole in the entire universe, which is described by the Kerr black hole. And the Kerr black hole contains only two free parameters, which are the mass and the angular momentum, because usually the electric charge, which is the third quantity that describes black holes, is regarded as negligible in astrophysical environments. It's important from the theoretical point of view, but plays no role in astrophysical environments. So all good. This is the clear neat prediction of the theory, and we have observational evidence of the existence of this object. However, there is a problem of theoretical origin with the Kerr solution. And this problem is unavoidable and is defined by the presence of a singularity in the interior of the Kerr black hole. In the interior means covered by its event horizon. It's a problem of theoretical nature because we cannot prove with any means what is inside the event horizon in such a way that tells us information about it. So it's a prediction of the theory. So the theory that predicts this object as real astrophysical objects at the same time predicts something that is happening in the physical that is happening in the black hole, inside the black holes. And this something is the singularity, and singularity is canonically characterized by a basic concept which is called geodesic completeness. Geodesic completeness means that in general relativity, geodesics are associated on the one hand, when we are dealing with timeline geodesics, with the motion of physical observers, either in free fall. By, on the other hand, the motion of light rays and also the gravitational waves are described by null geodesics. And because of that, they are also linked to the transmission of information. And the geodesic completeness principle demands that in a physically reasonable space-time, these geodesics, both sets of geodesics, should be complete for all observers and for all space-times in all circumstances. Because the paths of physical observers should be indefinitely extended both to the future and to the past, and information, as given by null trajectories, should never cease to be present. So this condition of geodesic completeness guarantees that physical observers will always find a well-behaved manifold in which to propagate, and that information is always conserved. Classical. Problem is that there is a set of theorems tell us that if a set of three conditions hold at the same time, which is the null energy condition, because this is linked to the null congruence condition of the focusing on geodesics, event horizon is present, and a problem of initial data is well posed. This is a version of the theorems for black holes, but there is also a version for cosmology. And these three conditions happens in black holes, then at least there is a one geodesic that is incomplete. And this cannot be, because if the geodesic that is incomplete is null, then we lose information, we lose the propagation of light rays and gravitational waves. It's not that we cannot predict, it's that the space-time, these trajectories run out of manifold in which to propagate. Okay, there is a kind of hole in the theory, and the same happens with time-like observers. So as if our space-time contains incomplete geodesics, so then predictability and determinism are immediately threatened. And this is what happens with black holes. They are unavoidable singular. What I mean avoidable means that it doesn't matter what are the particular mass and charge or the particular process of formation or the particular type of astrophysical type of black hole, they always contain a singularity. And this cannot be. So there is something wrong inside the theory, which is predicted by the same theory. So in some sense, the general relativity contains its own demise. So it means that we need to do something to preserve the observational accuracy of the theory for black holes, while at the same time look for ways of getting rid of the singularities. So this is the theoretical basis for modifying the Kerr solution. Problem is that as soon as you accept the possibility of modifying the Kerr solution, then there are plenty of options you can look at. On the one hand, you can look for modified black holes, meaning black holes that are not described solely by mass and angular momentum according to the description provided by general relativity. For instance, these new black holes may contain new hairs, meaning there are new parameters viewed as hairs that arise when you consider specific matter fields coupled to gravity, such as scalar fields, or there could be new parameters associated to upgraded description of gravitational interaction. It can be string theory, quantum gravity, or more generally, modified theories of gravity of different sorts. At the same time, there could be other objects in the cosmic zoo that does not contain even horizons. It means ultra-compact objects that closely resemble black holes. Because of that, they can pass as disguised black holes. That's why they are usually called black hole mimickers, but they don't have horizon. So there are potentially observations that could allow us to discriminate between these two types of objects, black holes or black hole mimickers. And there are plenty of them suggested in the literature. Two of the more popular ones will be wormholes and boson or Proc stars. So then, joining this effort of observations and theory, we have problems on both sides. On the theory side, we have a general agreement that there is something wrong in the theory of general relativity that probably will require modifications on its ultraviolet side, meaning in the strong field regime. So almost everybody agrees that there are modifications required by the theory in such a regime. But nobody agrees on how exactly such modifications should look like, or what the new theory of gravity should be expected to do, besides perhaps removing space-time singularities. On the other hand, in the phenomenology side, we question ourselves about how to better employ the tools of multi-messenger astronomy with light rays, gravitational waves, and neutrinos to study observational discriminators between any object which is not Kerr, be a modified black hole or a black hole mimicker, and the Kerr solution. And this is the context in which my research on this site is framed. Our aim of myself and my collaborators, also other sectors of the community, is to build models of black holes in modified gravity, meaning extending general relativity according to some prescription or some new principles, resolve in a natural way the singularities that general relativity black holes have. I will explain what means naturally. And then these new objects, these new black holes, to connect them with observational predictions and try to look for places in which we can seek traces of differences between general relativity predictions, the predictions of the Kerr solutions, and the predictions of the new solutions. So this is the scope in which my research is moving. So there are several, the theory side, there is much more ideas, basically because we have been doing this for longer, but we are catching up, or the community is catching up at the phenomenology side, basically because we have new observational devices. So in the theory side, I'm going to present a particular proposal, perhaps is the one I like the most, which is based on a class or a formulation of gravity in which it's not assumed, I'm going to say that it's assumed that metric and affine connection to be independent. Actually, it's the other way around. We typically assume that metric and connection are related because in general relativity, the connection can be given by the Christoffel symbols or the metric tensor. So in that sense, the connection is a secondary object, can be always removed in favor of the metric. But demanding this principle to hold beyond general relativity is an assumption. So what we do actually is to remove this assumption. And when you do this, generally, one ends up into the field of metric affine theories of gravity. So theories of gravity in which metric and affine are independent fields. Okay. Sometimes this is called the Palatini approach, but the Palatini is a misleading word because it's usually employed in the literature as an alternative way of deriving the Einstein equations for the Einstein-Hilbert action by performing independent variations of the metric and the connection. And because of the fact that in general relativity, metric and connection are related, at the end of the day, it doesn't matter whether you set metric and connection to be compatible at the beginning, or you make independent variations, and then the equations for the connection tells you that actually the connection is the Levi-Civita connection of the metric. So whatever way you choose, you end up into the same result. Okay, so general relativity link metric and connection in a specific way. Now, once you move away from general relativity, for instance, you consider a theory of gravity, which is constructed out of contractions of the metric of the Ricci tensor. This is something that we call Ricci-based gravities because we consider the Ricci tensor. We don't consider at this stage yet the Riemann tensor, only the Ricci. And we build contractions. Obviously, a contraction that you can build is the metric with the Ricci tensor to build the curvature scalar. So if you consider a function of the curvature scalar, you end up into the f of r formulation of gravity. Okay, but in this case, this is the formulation, the Palatini formulation of f of r gravity. You can formulate f of r gravity setting the connection to be given by the Levi-Civita connection of the metric, making this assumption ad hoc. But if you don't do that, if you allow metric and connection to be independent, then you have the metric affine or the Palatini version of the f of r theory. And the field equations in such a case for f of r gravity are not the same as the field equations of the usual metric formulation of f of r gravity, as opposed to what happens in general relativity, in which these two approaches give the same result. As long as you are outside general relativity, this no longer happens. And this no longer happens for f of r gravity or for other contractions of the Ricci tensor, such as the Ricci tensor with itself, the f of r nu approach to gravity. So we start with this thing. We build an action with the usual minimal coupling of the metric with the matter fields and the matter sector. There are several caveats because you can have torsion, but as long as you have boson, torsion can be always removed out of the game. So it's completely equivalent with setting torsion to 0 at the beginning. That won't be the case if we consider fermions, which is not the case. And our actions contain only the symmetric part of the Ricci tensor. Otherwise, if you consider the antisymmetric part, then your theory contains gauge line instabilities and things get much messier. So we don't want that. There is a technical solution to that, but the resulting theory is much more complicated and unnatural than this version with the symmetric part of the Ricci tensor. Okay, so we can build many different theories of gravity. Does not need to be direct contractions of the Ricci tensor with the metric. Can appear any scalar out of the metric and the Ricci tensor makes a good action. For instance, the determinantal proposal of Born-Infeld gravity, which you have the determinant of the G mu plus some constant times the R mu with proper contour terms. So it also gives you something which is well defined. Okay, so there are proposals that run away down quadratic gravity and things like that. Okay, good property of these theories is the fact that the field equations of the theory, which are obtained by independent variations of the action with respect to the method and to the connection, read something like this. And these equations look like what you have in general relativity. On the left-hand side, you have the Einstein tensor of some new metric that I call here Q. I will explain now what is this Q. On the right-hand side, you have the energy momentum tensor, but you have also other objects. You have the trace of the energy momentum tensor. You have the Lagrangian, the gravity Lagrangian itself here, and you also have some objects related to the determinant of a matrix. Now, what is this matrix? This matrix and this metric Q comes from the fact that there is another set of equations related to the field equations for the connection. When you do this, you get a complicated set of equations, but that you can always rewrite as this equation that appears here. This equation tells you the compatibility of the connection that appears in the covariant derivative with a new metric Q that we introduced somewhat by hand there. And we can do this because the structure of the metric field equations tell us that you can prove that the metric G that appears in the definition of the gravitational axiom, meaning here, can be related with this effective metric that plays the role of the metric of connection compatibility condition via some kind of matrix, which we call it as the deformation matrix. And importantly, this matrix can be shown to be a function of the matter fields and the metric G, meaning that you can always write Q as a function of G and the matter fields all the way around. In other words, on the right-hand side of the field equations, everything that appears here can be rewritten as a function of Q and as a function of the matter fields, meaning that you have a sort of modified Einstein field equations for a modified matter sector on the right-hand side. Okay. This is more or less general, but with the specific samples of F of R theory, things are quite simple. Okay, so and it's even with Born-Infeld gravity, I will explain next. Okay, the important point here, and you can trust me about this, is that you can rewrite the Einstein equations of the Einstein equation for a new metric Q, coupled to some sets of modified matter fields on the right. And once you solve these equations for the effective metric Q, you can obtain the space-time metric, the one we are interested in because it will be the one that describes our black holes, by inverting this relation numerically, so probably. But the problem has a solution. Okay. Another important thing, because of these properties, these theories will always yield second-order field equations without ghosts, without extra propagating degrees of freedom, and it's immediately compatible with solar system tests and gravitational wave observations because they belong to the weak field regime. And in the weak field regime, things behave exactly like in GR in these theories. There are no new fields, no scalar fields propagating in your space-time. And it's actually possible to obtain solutions of black hole time in actual analytical form, both for spherically symmetric spacetimes and for rotating spacetimes, according to some of the techniques we have been developing. Okay? But let's take one step back.
Sorry, Diego,
Yes.
one question. I have a question.
Yes.
So if you consider vacuum, do the theory recover GR?
It recovers GR plus a cosmological constant term.
For all RPG, you mean?
Yeah, for all theories.
Okay.
Basically, because in vacuum, the relation between these two metrics is trivial.
Mm-hmm.
It's times a constant.
Okay.
So everything is the same. So the two metrics are the same modulo a constant.
Okay.
Depending on the value of the constant, you will get a non-vanishing cosmological constant or not. But everything looks like in GR. That's why it passes naturally the weak field test, in which we care about the motion of bodies around black hole vacuum black hole metrics.
Okay, thank you.
Okay, so that's it. Okay, so one step back, because not to focus our goal here, we intended our solutions to solve singularities. And we identify singularities as geodesic incompleteness, meaning geodesics that are incomplete. So if we consider a very general spherically symmetric spacetime with a non-vanishing radial function, the geodesic equation looks like this. So this equation needs to provide us with a continuum from minus infinity to plus infinity of the affine parameter that appears here in this equation. Typically, for all solutions found so far, the RBG geometry will be encoded in two new functions that appear here defined in this way. When you introduce these two functions whose explicit forms depends on the theory of gravity and theory of matter fields are introduced in this equation, typically the geodesics that have problems in general relativity are null radial geodesics. They have problems in Schwarzschild, they have problems in Dresden-Rostock, and they have problems in Kerr. So we are interested in knowing how these functions should behave in order for the affine parameter to be completely complete. And everything revolves about the behavior of this function that appears here and the relation between this x coordinate that appears here and this radial function. In general relativity, this thing is 1. Okay, so at the end of the day, you get that this parameter ends at some finite point. And this is the basis, this is the core of the singularity theorems telling you that why this solution is singular. Actually proving the Schwarzschild solution is geodesically incomplete for null radial geodesics is very simple. It's one line of computation. In conceptual terms, there are two ways of removing the singularity. This on the right hand side will be more canonical because we are familiar to it because of the possibilities offered by wormholes. In wormholes, the radial function does not get to a zero value at the center of the object, but instead gets to a finite value, allowing the re-expand of geodesics through the wormhole to the other side. So while in general relativity black holes, geodesics get to the center of the black hole in finite affine time, and there is no possibility of further extension because the solution ends there. In wormholes, you can extend this thing through the throat. Obviously, wormholes are supported by matter fields violating energy conditions, but this is true only in general relativity. If we move away from general relativity, like we are doing here with these RBE theories, this obstruction is lifted. You could have, and actually you do have, wormholes that do not violate energy conditions. So this mechanism is viable in principle. On the second mechanism, instead of expanding or extending the space-time one way or another at the conflictive point, what we do here is to make the potentially problematic region in which there is the incompleteness of geodesics to drift away to asymptotic infinity, meaning that every geodesics that will get to the center of the black hole in general relativity at finite proper time, here will get some modification and never get to the center, despite the fact that the affine parameter is extended to all possible values from minus infinity to plus infinity. Okay, so in this case, the behavior of curvature scalars that can be divergent at the center is irrelevant because geodesics will never interact to it. They will be complete to the future and to the past. We will never get to the center. On the other case, geodesics can be extended, but that does not mean that curvature will be finite there. Actually, in most cases, will be infinite. Curvature will grow up, but that doesn't mean that observers will get destroyed because of the presence of infinite tidal forces. Actually, observers can pass because the curvature divergence is so mild that it do not destroy physical observers, basically because the tidal forces act upon integrals of the curvature. So if the curvature is sufficiently small on its divergence, they do not necessarily destroy observers. But that's a different story that belongs to the past about how to resolve the singularity. Okay, so you can go to these references to check exactly how this works. Now, I'm more interested, for the sake of this talk, of connecting this with observations. And to do this, I consider here an explicit example. Okay, so there are a lot of recursion definitions here. You don't need to worry about that. This is just a modification of general relativity via this square root modification. This is usually called Born-Infeld gravity because its resemblance with Born-Infeld electromagnetism is actually a modification of quadratic curvature type as followed by expansion of the theory in series of the curvature. So it can be seen as quadratic gravity, just to simplify things. Now, the important point is not these technical details. I just plug it here for completeness. It's just to tell you that there is an analytical solution found out of this theory coupled to Maxwell electrodynamics. So matter fields satisfying energy conditions. So everything good. So we have a theory of gravity which we will define that recovers general relativity and weak fields. Matters are perfectly reasonable, and we get an analytical solution. And this analytical solution behaves like Dresden-Dostrom asymptotically, but near the center of the solution, instead of having a singularity, we have a wormhole structure. But this wormhole is not supported by exotic matter sources because the matter source is a standard electromagnetic field that satisfies energy conditions. But we avoid the singularity without violation of energy conditions. And as I said, curvature scalars might blow up at the center. Generically, they will. But it doesn't matter. Analysis of the behavior of physical observers tell us that they stand fine. They can survive the counter with a third of the wormhole. And there is much more flexibility in terms of structures of horizons. We can have two horizons, like Dresden-Dostrom, as a single non-degenerate horizon like in Schwarzschild, or even non-horizons. So in this theory, we can have horizonless compact objects supported by matter fields satisfying standard any conditions. Now, at this point, you can argue that this is an oversimplification of reality because we are dealing with spherically symmetric black holes. But the fact is that we already have rotating black holes. Now, the key point here in this analysis is that this rotating black hole that I present here, which is also for Born-Infeld gravity coupled to an electromagnetic field, so it's the extension of the previous solution to the rotating case, is not obtained by direct resolution of the field equation, because this is extremely tough to do, even almost impossible. But we found a shortcut to do this thing, which is basically to make use of the resemblance of this thing with usual Einstein equations. So this looks like Einstein equations. So if I redefine all this stuff like a new energy momentum tensor, so these are Einstein equations for a new energy momentum tensor and for a new metric. Okay, so this is like having general relativity coupled to a new set of matter fields. The metric that appears here is the Q. That's okay. But because of this relation that appears here between the Q and the G, we can work out the relation between Q and G in a very generic way, algebraically. And at the same time, using this relation, we can work out the relation between the gravitational framework that we already have and the matter framework. These matter fields are related to this one via algebraic transformations. So everything is related to this, meaning that if I have a solution of general relativity coupled to a set of matter fields, I can have an equivalent solution of RBG coupled to a different set of matter fields of the same nature, but with different functional dependence on its variables. So now, if I want to get the solution of Born-Infeld gravity coupled to Maxwell for rotation, I just need to work out these algebraic relations to find general relativity coupled to some new matter fields. These new matter fields, the dependence of the functional dependence can be extremely complicated. But maybe we are lucky enough and this solution has been worked out in the literature of general relativity. And as it happens, this is the case. The solution of RBG plus Maxwell maps into general relativity plus some nonlinear model of electrodynamics, whose solution is known. So we can use that known solution to work out this algebraic transformation from this side to this one and find the extra solution. And once you have the extra solution on this side, it's much simpler, for instance, via Mathematica, to check that it actually satisfies the field equation, which it does. So we verified, like some kind of shortcut trick, like the Newman-Janes trick. We get to some form of the line element, and then we verify that it satisfies the equation. Okay? So we have a rotating black hole. Okay, so equipped with the spherically symmetric black hole with no singularities and rotating black holes with no singularities, we can do phenomenology of different types. So I will go for it. I'm going to show you a couple of things. The first thing we can do, again, I'm working with Born-Infeld gravity coupled to Maxwell, is to use the constraints from the S2 star, which is the closest, one of the stars that orbits Sagittarius A star, the supermassive black hole, which is believed to be at the center of our own galaxy, and test several observables related to the orbits, and to the rate of the orbital precession. Why is this? Because this star has been tracked for 30 years up to a great precision. So if it happens that if we allow too large values of the Born-Infeld parameter, like here, then in measured time, the orbit of the object will have deviated from what we are observing. So this puts constraints upon this. And the same happens with the orbital precession. This pink region that we have here are the constraints that we have for gravity collaboration. And these are the cures that we have for different values of the electric charge and for the values of the Born-Infeld parameter. And as you can see, many of these regions are ruled out by observations. There's only some kind of tiny region here combining the Born-Infeld parameter and the radius that are compatible with data in this theory. But we can also do something else, which is to study gravitational waves, the predicted waveforms of these theories. And we can also study shadow images, depending on what we are interested in. The thing that we are much more developed are shadows. So this is why I'm presenting you this. So shadows means that a black hole is illuminated by this accretion disk, by the material that is surrounding the black hole and is falling towards the black hole. And because of gravitational friction, it hits, emits electromagnetic radiation that illuminates the black hole, meaning that those light rays are going to suffer gravitational deflection in the gravitational field of the black hole before getting to the observer. And this produces a characteristic image in our screen, which is composed of, for instance, these three models that I'm using. It predicts a kind of bright area surrounding a central blackness depression. And inserted into this bright area, there is some kind of, in some images, you can appreciate a boost of luminosity here and here. Here more extent, here is dimmer. This is due to the fact that photons that suffer very heavy gravitational deflections can turn more than one times around the black hole. When they arrive to our screen, they produce what is called a photon ring. Trajectory is highly bent in the space-time of the black hole. And because every space-time, in this case a black hole, every kind of black hole bends space-time in a different way, the properties of this photon ring are going to be slightly different, providing us with an opportunity to make tests of our favorite modifications of the cursors, like the one that I was proposing before. This is for spherical symmetry, but we can upgrade this to axial symmetry. Now, I don't know if any of you have been following my talk 1 hour ago, because I was talking in another meeting. I was explaining all this field in detail, okay? So this will be freely available in YouTube after a few days. So if you are interested in seeing exactly how we do this, I will be happy to provide the link of the YouTube recording, and you will be able to see how we do this. Actually, I have been talking, it's 3 talks of 1 hour and a half each. So it's almost 5 hours of talks about this thing. For the particular case, in particular of Palatini gravity, but can be adapted to other scenarios. Okay, continuing with this talk, we can use these images to measure some of the main observables, which is the features of the photon ring, location, number of them, luminosities, widths, and so on, and the size of the central region, the size of the shadow, which is something that the Event Horizon Telescope is already doing. But there can be many other players in the game, because we talked at the beginning of my presentation that there are many other objects proposed in the algebra: boson stars, Broca stars, Graval stars, wormholes, and so on. So there could be many other features of these objects that could yield two observational discriminators compared to black holes. In particular, a proposal that was introduced here in this paper deals as double photon spheres, which can be generated, for instance, in asymmetric wormholes, meaning wormholes that are different on each side of the throat. So in this reference, they build some of these objects. The typical potential, effective potential that you get is something like this. And this allows you to produce, in addition to this structure that I have here, this photon ring associated to the maximum of the effective potential. Since there are two maximum of the potential, a local minimum, a local maximum one, there could be two different sets of photon rings associated to each maximum, producing something which pictorially is depicted here. Okay, these are not true colors; these are true colors. Okay, but we didn't run the simulation yet to this case. It's something we still have to do. Okay, so here we provide a theoretical basis to this thing. But this will provide a characteristic signal of this scenario, which is completely different than what you expect in a black hole scenario, meaning that there are clean observational discriminators between horizonless compact objects, for instance, this one, and black holes, something that is not that easy to find when you have modified black holes, because basically the images are very similar to each other. Okay. This is a different case. For instance, a traversable wormhole in Born-Infeld gravity. Okay. We can also do the same with boson stars and so kind of. For instance, this is the case in which we consider something which has an absolute maximum, local maximum of the effective potential, but at the same time, an infinite potential barrier at the center. So we will get something like this. As you can see here, inner to the image, there are many new photon rings that do not appear in canonical black holes, something like this. Here we have 1, 2, and 3 peaks. Here we have many. These are associated to something that has no horizons, basically because the additional peaks in a typical black hole spacetime are not present because the inner region of the black hole cannot be accessed to because there is a horizon. While here, for any other object in which you can access to the interior part of the object, new things could happen there because of the interaction with the effective potential in that region, producing images like these 3 images that are very different from a black hole. Actually, too different. These are not compatible with what we are seeing at the moment. Okay, so the message to take home, because I have been summarizing a lot of things here about maybe 10 years of research about this theme. First of all, metric and affine connection are independent entities. They are logically, conceptually, and mathematically independent entities. The fact that they are linked in general relativity in a specific way is a trademark of the theory that does not necessarily hold when we move away from the theory. There is no need to link each of them to satisfy any physical principle which has been measured today. When you do this, you get access to a new families of theories, which are Ricci-based gravity, which are mathematically consistent in the sense that they satisfy all the constraints, second-order field equations, no ghost. So all the typical problems that plague most modified gravity models are not present here, and they are automatically compatible with weak field limit tests. They predict, nonetheless, deviations in the strong field regime, particularly related to the fact that, or the way they solve the problem with singularities. Okay. At the same time, because of for astrophysical purposes, we need rotating black holes. We have developed methods allowing us to obtain exact analytical solutions of rotating type, provided that, one, we have the spherical symmetric counterpart, and second, we know in general relativity what matter fields it corresponds to. If we do know these 2 things, we can map that solution into RBGs. And this is good from the point of view of theory, but we need to make contact with observations. Here I have told you 2 things, one related to motion of these 2 stars and the field of shadows. I didn't talk anything about gravitational wave emission because as far as I know, nobody has done this in the literature yet. The only thing that has been done is propagation. If I remember, unless there is something I didn't spot in the literature, nobody has provided waveforms of rotating black holes in these theories of Palatini. They have done it in the metric approach for some theories. And there are other observational discriminators. For instance, in Palatini theories of gravity, the internal structure of stars may also change. And there are observations related to them, like what is called the limiting masses. These are the masses that determine the transition from one kind of compact star to another. For instance, from white dwarf to neutron star, or from giant planets to main sequence stars. General relativity gives a specific number, which is something like 0.08 solar masses, for an object to shine. This mass is modified in Palatini gravity. So that's another set of tests you can run with these things. Okay, that's all. Yes, well, this is the project based on multi-messenger astronomy and shadows that is funding me at the moment. I thank you very much for your attention. I will be happy to answer to any of the questions or to share any additional material with any of you who could be interested.
Thank you very much, Diego. Any questions from the audience? Maybe I can ask one. So it's a general question. So far the phenomenology done here is still based on, well, it's a class of theories, but it's still kind of theory-based analysis. So my question is that if we want to, like in your opinion, if you want to go if we want to do phenomenology, what should we do to go beyond like theory-based
That's
analysis? I
right.
mean, to promote the analysis to a more theory agnostic
That's right.
sense.
Yeah, I am also very in favor of this kind of things. To summarize in a single unified framework the kind of modification you get in these theories. Actually, it does not need to be in these theories, it can be completely in general. What kind of new features we could expect the modified gravity about the new shape of the metric functions, solving the problems that general relativity has, in this case singularities. So what is the general shape or the most general line element with the different features? And they go and then implement the predictions of these new metrics in different scenarios. They have been doing this for years in the case of gravitational wave radiation, proposing parameterized metrics by a number of coefficients at different prescriptions that could be solutions of different theories of gravity. And then run the tests to constrain these parameters. Same thing could be done in other contexts. Could be done in the orbital motion around supermassive black holes and could be done in the shadows. To best of my knowledge, this has not been done yet. So it will be a good opportunity. Another good opportunity will be to make cross tests, in the sense, make parameterized solutions and apply them to different scenarios with different messengers to see how these messengers, how this information combine to constrain your theory, to constrain the parameters of your theory. A different thing will be this line, these new metrics will be a solution of what theory? That will be a different thing. We are running now in the first approach, get the specific solutions of theories that are already under control to see what kind of modifications we can get. If we do the same thing with several theories and we get to see conceptually similar modifications, then we can unify this under a single approach to see, okay, these theories seems to predict for different theories and different matters that the new metric will behave this way. Okay, get parameterized such a metric and then go to the constraint and how does that react into the parameters of your theories.
Thank you very much. Okay, so one hands up. Evelyn, please ask your question.
Hi, thanks for a very nice talk. My question is about Ricci-based gravities.
Yes.
Do you expect to have more than two polarization modes in the gravitational waves?
No, that's not possible in these theories because these gravitational waves belong to the linearized regime. And in the linearized regime, everything is the same as in general relativity. Okay, so for the propagation of two polarization waves. Now, because the black holes in this theory are going to be different, the generation in the merger of gravitational waves is going to be different. So the templates in the generation are going to be different, meaning that when you run your simulation in general relativity to reconstruct the black holes that are producing the wave, this is in general relativity. This same reconstruction made in the context of the RBG gravities, depending on the theory of gravity you are considering, will provide a different couple of black holes with different mass angular momentum in general relativity. In such a case, this is a problem because it's degenerate. Such kind of information do not rule out the theory because it can disguise itself into that. But the number of polarization will be always two. There are no, in this approach. If you start adding new things to the theory, things can be different. If you consider torsion or you consider antisymmetric paradox tensor or other combinations or extensions of the theory to the Kretschmann, things could be different, but not in this approach. Actually, we favor this approach because, as opposed to most theories of gravity, enters not in conflict with two polarizations, which is a core of the general relativity, and that's what apparently observation is telling us at the moment.
Any other questions? So Diego, do you have the Penrose diagram of the rotating solution in?
No, not that one. We never write it in the paper.
So then do you know
the spherically symmetric case we do, but not in the rotating?
Because I'm curious about how for example, the singularity structure in Kerr-Newman would be changed in this theory.
Yeah, I will too. But since we went after phenomenology, we left that bit a little bit behind.
Okay.
So.
Any other questions? If no, then maybe we can end the official session of the seminar. Let me stop recording.